So example 1, given t of x equals x squared plus 3x minus 10 divided by x squared plus 8x plus 15, let's find the following and then we'll sketch this graph. So remember, the first thing to do is look at the denominator of t of x before we do anything and find the zeros of the denominator so that we can write out the domain. We can declare what the domain is. So looking at x squared plus 8x plus 15, let's factor that before we read the excluded values. So it looks like we'll have x plus 5 times x plus 3. That's the denominator in factored form. We're going to solve that. So we can read that x equals -5 or -3 are excluded values. So our domain in interval notation will be -infinity to -5, jump over -5, then we can travel all the way to -3, but we have to jump over -3, and then we can keep on keeping on until infinity. Now for holes in vertical asymptotes. Now that's when we want to go and factor both numerator and denominator. We've already done the factoring of the denominator, so I'll just jot it down below here. Now let's factor the numerator. Well, let's see, we have a positive 3x and a negative 10, so I'm going to say x plus 5 times x minus 2. That's the numerator in factored form. And yes, we do have a common factor of x plus 5. So where's our holes? Well, we're going to solve x plus 5 equals 0. Of course, we could have read that at x equals -5. There will be a hole. Now we're going to plug that value into the reduced function. So I'll just write the reduced function over here, or reduced form. Y equals x minus 2, that's all that's left in the numerator, over x plus 3. So that's the reduced function. Remember, these functions will look the same except for the holes. So the shapes will be the same, behaviors around asymptotes will be the same, but there will be a hole in t of x, and there will not be a hole in the reduced function. We're just using it for the rest of the analysis. So I need to plug in x equals -5 into the reduced function. So I'll have -5 minus 2 over -5 plus 3. And what does that give me? It gives me -7 over -2. So I have a positive 7/2 for the y value. So I have a hole at -5 and 7/2. Now for the vertical asymptote, we look at the denominator of the reduced function and solve that. So we have x plus 3 equals 0. So x equals -3 is a vertical asymptote. So we have vertical asymptote, we have a hole, and so far we have the domain. Now let's look at the degrees of the numerator and the denominator and compare them. So when I look at the reduced function, I have the degree of 1 and in the denominator and a degree of 1 in the numerator. So I just have to compare. So I'm just going to bring this down here. I'm going to compare the leading coefficients of 1 over 1, that ratio, because remember, when we don't write it, there's a 1 in front of the x here and a 1 in front of the x here. So I have y equals 1. So I have a horizontal asymptote of y equals 1. Now on to intercepts. This is where we have a little bit of algebra to do. So we're going to work with the reduced function just because it's a little easier, it's a little less work. We could go back up to the original t of x, but we're going to go ahead and find the y-intercepts by plugging in x equals 0. So we're going to say y equals 0 minus 2 over 0 plus 3. So we have a y-intercept of negative 2/3. So as a coordinate pair, that's 0, negative 2/3. And then we only have to look at the numerator of the reduced form and solve that, because that would be setting it equal to 0. So x minus 2 equal to 0. We could write the x plus 3, but it's not necessary. We just have to find the zeros of the numerator. So that implies that x equals positive 2. So the coordinates would be 2, 0. So I have both an x and a y-intercept. So this is our x-intercepts, is by plugging in 0 for y. And let's sketch the graph, and then we'll read the graph to describe the behavior near the vertical asymptotes and its end behavior. So with all of the information above, and you'll have to look at your paper because now the screen doesn't show it so well anymore, I'm first going to sketch the asymptotes. So at x equals negative 3, I'm going to just demonstrate with a dashed line that I have a boundary here, and that function will never cross that vertical asymptote. So we just do that with a dashed line. We also do a dashed line for the horizontal asymptote of y equals 1. So we kind of have 4 sections of the graph here. I have a little bit more information. I have a y-intercept of 0, negative 2/3. Maybe that's about there. So 0, negative 2/3. And I have an x-intercept of 2, 0. So I'll go ahead and jot that down too. So I know, let's look at this. Now I know that my function is bound by y equals 1 and x equals negative 3, and I cross through these two values. So I kind of have to show that this branch lives between x equals negative 3 and below y equals 1, because it can't be both above and below because it wouldn't be a function. And then on the other side of x equals negative 3, I do have something I can document in that branch, and that is the whole of negative 5, 7/2. So that whole is negative 5, 7/2. And also I have to live between y equals 1 and x equals negative 3. And other than picking up my pencil to jump over this hole, I'm not going to have to do anything else but stay between and above y equals 1 and less than x equals negative 3. So that's kind of your first view of taking all of that analysis that you do algebraically with the equation of the function and getting it to the picture on a graph of that function. So now let's read the end behavior. As x approaches negative 3 from the left, f of x approaches positive infinity. As x approaches negative 3 from the right, f of x approaches negative infinity. And the end behavior, as x goes both to negative infinity and positive infinity, f of x approaches 1. On the right, it approaches 1 from below y equals 1, and on the left, it approaches 1 from above y equals 1.